Can you hear me well? I think yes. Okay. So this project is one that Cording gave me very early on, and I used it a little bit as a sort of as a playing field to test. I mean, to get into the PhD and to test symmetry reduction techniques and how to do this a bit more automatic, because I will talk about this, but automatically doing this fully automatically is kind of hard in terms of complexity. And so whether you care about the combinatorics of this or not, it doesn't matter. In the end, you will have at least picked up a little bit of a crash course in symmetry reduction. So, yeah, okay. I will first, again, go a bit through the combinatorics and then crash course symmetry reduction. And then actually only the last slide is something a bit new, but I don't feel very comfortable yet presenting what I'm trying because it's not working yet. We don't get to the goal where we want to go, but we'll see. Okay. So there's also three new Hungarians in this talk. So we start with the Chimeredis theorem. We have a prime number P. We work in the finite field in P elements. And here we look at arithmetic progressions. So you start with one element in FP, and you choose a sort of a distance, and then you go k times the distance, and then you have an arithmetic progression. This thing called a k-term arithmetic progression. The Erdo-Tura constant is the largest cardinality of a subset of FP that does not contain any arithmetic progressions. And Chimeredi proved in 75 that this should be a bit more up. But anyway, that this number, this Erdo-Tura constant, grows weaker than linear. And the goal of this project is a little bit to obtain tight bounds on this in terms of actual computations, because there's a lot of asymptotic results, and it's a very interesting problem for the reasons that I will explain after this. But we try to make it a bit more concrete, and we try to go as far as we can in P. Okay, so this is coming from a very simple looking conjecture, which turns out to be very hard. So if you take a subset of the natural numbers, you say that it's large if the sum of the reciprocals here is diverging, the series. And if you have a large such subset, the conjecture is that every such subset contains arbitrary long arithmetic progressions. So for any k, you can find arithmetic progressions in that subset. And Chimeredi's theorem is a weaker version of this. It's a bit weaker because, is there chalk somewhere? No. It's a bit weaker because this is equivalent to saying not that the subset is large, but that the subset has positive density, which means that the limit of all the numbers up to a given n divided by n is positive. Then you have positive density. And so this is a bit weaker, but the proof was very, very successful in terms of generating new techniques for combinatorics. So from that, from that perspective, it was very, very successful. And right after this proof came out, Erdo set a bounty on this problem for $3,000. It's still open, so if somebody is very interested, give it a try. And he was so desperate to solve it that he increased it even. But there's not a lot of hope. For instance, Green and Tau is the famous theorem that there's arbitrary arithmetic progressions in the primes. This is only a special case of this conjecture, because the primes are large because the sums of reciprocals, they diverge, but they have density 0. So what they have to do is they sort of have to shift to find techniques to move Chimeredi's theorem to this context, which it doesn't hold usually. but it's a similar technique. So it's still interesting to find these, to find good rates on this number. And there was even like, so the case k equals 3 is proven, and this was exactly done like this. So Bloom in 2016, they improved the bounds on the growth rate, and with this they could obtain the conjecture for k equals 3, but that's it so far. Okay. And then, so what we're going to do is we're going to formulate this as a polynomial optimization problem, and then we're going to throw the Lasserre hierarchy on it. And this is how we do it. So first we identify subsets. Sorry. And we identify subsets by indicator vectors in 0, 1 to the p, right? So if an element u is in the subset, we set the uth component of this vector to 1, otherwise 0. And then we can formulate the number of arithmetic progressions in k terms as a polynomial by saying that, so the sum is over all arithmetic progressions, which are just indexed by the starting point and by the distance. And I just multiply all the components of x that would belong to the arithmetic progression. So if one of these is missing, this term is 0, and we don't have a contribution. So this is exactly the number. And then what Schilland did in his PhD thesis was he wrote this down like this, and he introduced this number w, which is the minimum over all subsets of fixed density D. So the minimum over of the number of arithmetic progressions that are contained in all subsets of cardinality D. And if you do this, you quickly observe that this is exactly what, this allows to reformulate this constant, because the largest D, such that this is 0, is exactly the Erdo-Sturm constant, in the sense it's the largest subset that does not contain any. It's like an intersection, I think. Yeah. Is that good so far? Yes. We do it modulo p because it's much easier, because there's no wrapping, or I mean, there's wrapping, but there's no contractions and these kinds of things. Okay, and so this is how it would look like. So on the x-axis here you have the densities. On the y-axis you have the w, the values for w. This is for p equals 13, and the red dot is exactly the Erdo-Sturm constant. So you have, it's obviously it's growing monotonously. And in the beginning you have a bunch of zeros until you find your constant, then it's going up. So our goal will be to lower bound this curve using the Lasserre hierarchy. And so if you write this down as a in the moment language, to so somehow we have a pop and p Boolean variables, so x0 to x p minus 1, I think I call them, and the monomials are now just indexed by multi-indices that are just 0 or 1. We have a degree k minimization objective, right? This is this AP of x function that I defined earlier. That's degree k, and we have a single degree 1 equality constraint, or 2 inequality constraints if you want to put it nice in the framework, which I will do here. So it looks kind of easy, but so then you go ahead and you formulate the usual semi-definite program from the Lasserre hierarchy. This is the level is t. We need that 2t must be larger than the largest degree that appears, which is k. And our goal will be to use level 2 as good as we can. We want to come to 2027. That's because when Quentin gave me the draft, he because it's been a long time ago, and there the next prime year was 2017, I think. That was close, was it? Yeah. And so now we want to go to the next one. So we have a bit of time left, but the longer we wait, I mean, it's not getting any better. Yeah, so already there, the combinatorial moment matrices, they're huge. So they're 2 million by 2 million matrices. And the dimension of these vectors, which are, I mean, for like up to degree 4, with these number of variables, it's enormous, it's almost a trillion. So there's no way that this is going to work. So the solution, yes, maybe for a small example, this is how the relaxation looks like when you actually compute it. So there's the blue one, the exact value here. And the relaxed value is it looks kind of golden. I think it was yellow before. Anyway, on top, it looks kind of good. There is a little bit, so I cheated a little bit here. I should have plotted like the logarithmic distance or something, because there's a bunch of negative values here, and they're kind of problematic, right? Because right now we're lucky because the next one is positive, but it could go on like a little bit negative like this and then go up, and then we wouldn't know exactly where the constant is. Yeah, but so this gave us hope that this might actually work. And then the step to make it actually computationally tractable is using symmetry reduction. And there's a very big symmetry group that is acting on this problem, which is the affine group of this field. And it's just the AX plus B group, in the sense that it's translations and dilations and then everything in between. So this is generated by the translation by 1 and the dilation by some generator of the dilation group, which is the cyclic group in p-1 elements. You can also write it down as a semi-direct product. And this is acting on the variables just by permuting the indices according to translation and dilation, which sorry, so it's acting on the variables. From this action on the variables, you also get an action on the monomials, and from there you also get a representation in the end. But the key point is that arithmetic progressions are mapped to arithmetic progressions, because when you take one and you shift it around in this sort of cyclotomic field, you don't change any. It's still an arithmetic progression. When you scale every term of it, you also don't do anything, but that's because we have a prime field, like a prime order field, and everything works nicely. Yes, and then we get the induced representation on the, let's say, on the space of Boolean, on the Boolean polynomial ring in p variables, and this is what we will be looking at in a minute. Okay, so now we look at ways on how to exploit these symmetries as good as we can. So the first way is using invariant theory. And the idea is to use this invariant version of Putina's Positivstellensatz. Which says that, okay, if you have a finite group which is acting on on a polynomial ring in n variables, and we have a semi-algebraic set that is also where the defining polynomials are invariant under the group action and satisfy the usual Archimedean condition. And then we want to characterize these linear functionals that are in this case also just invariant under the action of the group. And so the statement is that if we define these by linear forms that we get by applying the linear functional not directly to the polynomials now, but to the averaging over the whole group times the localizing monomial maybe, then then this linear functional that we had before is exactly integration with respect to probability measure, which is also invariant under the group action, if and only if all these bilinear forms here are PSD. There's nothing unexpected, just the translation to the case in which there's a group acting. But the cool thing is that in this case, so this is a invariant linear functional. This gamma j, they're invariant by assumption. And this function here, this term here is basically just a Reynolds operator. This is the projection onto the invariant ring. So this whole thing is just dependent on the values on the invariant ring. So this is the first big reduction, because now we can work, at least in terms of the number of variables that we have, on the invariant ring. It would look like, we can do an example, for instance, what that would mean in practice. So if we, maybe do it here. So if we take a, let's say, cyclic group in 3 elements, then we can define the normal moment matrix in, let's not do it Boolean, let's take a normal moment matrix, like this. Then we have terms, and here we have be like this and symmetric here. Then if we have the cyclic group acting just on the variables, just by cyclically shifting them, then this theorem tells us that actually we can reduce our the number of variables that we have just to the variables that are invariant under, sorry, that build one orbit under the group action. So for instance, these 3 here, so the 3 linear terms, they are shifting around, right? So all of these, they are mapped to the same, let's introduce a new variable. They are mapped to the same variable, let's say Z1. The same is true for the second, so the square terms here. They're all being cyclically shifted around. So we have another term, Z2. And these last 3 here, they're also being cyclically, I mean, this is the same, sorry, right? They're also cyclically shifting around. So they make up a new orbit, and we call this Z3. And so we reduced the problem already from 7, a lot of, like 10 variables to 4, which is already kind of cool. I mean, this is, a nice example, but this is the idea. What that means for the actual SDP in the end is that you, so I usually think about the SDP in dual form. So I think about it in this form, and what that means for the SDP in the end. Is it visible with the light? Is that the number of constraints that we see here is going down, which is good, because this is the first big step in an interior point solver, for instance, where they build these big Newton systems and they scale with the number of constraints there. So that's the first reduction. This is from invariant theory. The second one is from representation theory. And this is the this is block diagonalization. And this is a bit, so maybe I can say a word to the, so Henry, is Henry here? Yes. You spend a lot of time on finding a good algorithm to determine if 2 elements belong to the same orbit, right? So if you want to do this kind of things, big scale for very large groups, this is computationally very expensive generally. And you have to be a bit smart about doing this the naive way is probably not going to get you very far. Let's put it this way. So it's very nice to have these kinds of algorithms around to make this a bit faster. And the next sort of computationally hard part is the block diagonalization. So what we do is, we had this representation before. I complexify it now just to make things a bit easier, so we don't have to care about different types of irreducible representations. But it doesn't really matter for now. The goal is to take this representation and bring it into a block diagonal form, essentially. So we want to find a basis that implements this. Okay, the representation, we call it rho. We have a chi here. We take the n irreps of the group gamma, which was our affine group before. We say that like each of these irreps has a character k, as Gordian defined earlier. We have it's working on the space wk, and we have a dimension. So the space has dimension dk. And then the first thing that you can immediately compute usually is the multiplicities that will appear. And already, so when you know the degrees of your irreps and you computed these inner products, which is very cheap in comparison to what's coming, then you can already assess whether it even makes sense to start the computation. I mean, very practically speaking, right? So and then there's this nice sort of unique form of Marshall's theorem, where you can decompose your finite dimensional representation into a direct sum of isotopic components. So they are indexed by the irrep. So each isotopic component corresponds to exactly one irreducible representation. And in each of these components, you can even go further, and you can go down to multiplicity space, in the sense that if we know there's mk irreps, mk irreps of so the irrep rho k is appearing mk times, then you can get another internal decomposition according to the multiplicity. And these wkl will all be isomorphic to wk. So this is on the representation side. What we're interested in, though, is the commuting, let's say the gamma invariant endomorphisms, though, because this is where our moment matrix lives. And this is what we want to decompose. And on that side, it looks similar. We have a, we can decompose according to both irreps. And for each irrep, we have a sort of d to the k copies of multiplicity spaces. So d to the k, this is, think about it as a Kronecker product. D to the k copies of the exactly the commutators of sort of the simple, no, the other way around. Doesn't matter. You get the decomposition into multiplicity space times degree. Let's put it this way. And this you can compute explicitly by using these sort of well-known formulas. So the first one is a, this is called the isotypic projector, which takes a representation and is exactly the projector on the kth isotypic component, and it looks like this. Note that we have to sum over the whole group here, but actually, since the characters are they are class functions, so they are all the same in the same conjugacy class, we only actually have to sum with the conjugacy classes, so this is kind of okay. And then if you're able to write this down and then compute the column space of this one, or the image, and find a basis for the image, you already have the first sort of part found, which is for this direct sum, right? And then the next step, you can go and you can decompose this further. And you do this by sort of these intertwining isomorphisms. So the goal now is to construct isomorphisms between those omega WKL. And this is a bit more complicated because now we actually have to go down to the level of matrix representations. So you have to know, first of all your matrix representations of the irreps, so the character table isn't enough anymore. But also, you can't really simplify the sum. So this is usually where you need to be a bit smart, and you have to usually symmetry reduction paper would compute them out. Right? There's automatic techniques, but because of these reasons, they don't scale very well. And anyway, so when you do this, these two techniques together. So first you reduce the number of variables, and then you reduce the sort of the number of constraints. I will talk in dual form now, and the number of free variables that you have, right? Because you can block diagonalize the whole SDP. Then you can sometimes get something working. And in our case, so we started with, what was it? 2 million by 2 million dense matrices with almost 1 trillion constraints. And if we apply these techniques, so on the x-axis here you have the prime p, and on the y-axis you have just whatever I'm counting right now. So the number of constraints, which is the number of variables from, so the basis for the invariant ring up to the degree, a linear basis for the invariant ring up to the degree that you care about, is really okay. I mean, this is below like 10,000. This is doable to, you know, to our target prime, let's say. The matrix size doesn't change because we didn't do anything with it, but we did change the number of free variables that we have in those axes. And if they were dense, you would expect something like, what would you expect? Something like this, the square of this one, right? Which would be somewhere up here. But we did reduce it quite a bit. It's still a lot, I mean, it's still a lot of free variables, but since the next hard part in the interior point solver is this, this line testing for finding the next best PSD matrix that goes along in Newton directions. This is not really representative because actually the individual matrix sizes are much smaller. So this is computationally much more efficient than this huge dense matrix. I mean, orders, many orders of magnitude, much more efficient. And yeah, and so this is like the general idea of symmetry reduction. These are a few things that we use to improve this a bit more. So for instance, we have to for a given prime, we have to compute in all the D, right? So one thing that we can do, you can observe that actually with D, not much is changing in the SDP, and many solvers can sort of deal with this. For instance, MOSAIC, if you use the MOSAIC something API, then there is a way where sort of you change the parameter and it will re-optimize starting from the solution that you had last, and so this is quite efficient. We can use previous knowledge, so if we change P, there's relations between growing P, so we get lower bounds from that also, so this sort of determines where we can start with D for the next one. We get very cheap upper bounds by just sort of random sampling, right? This is really just, you plug in, you randomly sample these indicator vectors, let's say, with exactly 10 D ones, and then you just sample, and you get quite good upper bounds from this also, very fast, because it's super vectorized. And it seems like that first order methods, at least for the primes that we tested so far, give more or less the same results. We might investigate this a little bit further. But in terms of symmetry reduction, I think the most interesting part is the semi-direct product structure of the affine group, because for cyclic groups, it's really fast to compute isotypic components. So all the Arabs are one-dimensional in the complex case. So you don't have to deal with these intertwiners anyway. And you can just write down the isotypic projectors very fast. They're very sparse, very easy to compute. And you can also decide very fast if two things are in the same orbit. And this is the combinatorial model of necklaces. And there's very, very good algorithms for that. Another idea would be to sort of first apply only the cyclic group reduction. And then after that, since this group is very nice in sort of many senses, you can, I hope you can sort of recurse into the individual blocks that you get and apply whatever symmetries are left in those, so that you have decreased the whole problem size of symmetry reduction itself. This is what I hope, what I'm working on right now. And then there's also the Hydro group in there. And for the Hydro groups, there's also fast orbit checking methods. In this case, it's the medal of bracelets. If you're interested, you can look these terms up. And I mean, the representation here of the Hydro group is very well understood. So this might be an option. And yeah, the goal is the next prime. Let's see if we can make that happen. Thank you.
Thanks a lot for the nice lecture. Questions? So maybe I ask a question. So this, everything you explained was to solve the laser relaxation of order 2?
Yes.
That's, yeah.
Yes, because I mean, all the numbers, I mean,
it's already,
yes, it's all okay.
Don't take it as a... And what reduction, so you had, without symmetry reduction, you have an enormous bit matrix.
Yes.
After that, you get a block diagonal matrix.
Yes.
And what is the largest size of a block? About to get an idea of.
Yes, it will be in the order of P.
Oh, okay.
It's still big.
P, and the previous one was P squared, or even more. Huh?
Yeah, I mean, the previous one, yes, I mean, it's the second order relaxation, so it's P squared.
P squared. Okay, no, but it's.
Yes, I mean, it's an important step to
yes. I think you cannot go below P, huh?
No, yeah, I'm not sure why. Maybe, we'll see. There's some, I don't know, maybe smarter bases or something like this where we can.
So it's already a lot of work to compute the block diagonal.
Yes, it is exactly the point,
what
right?
You explained, huh?
Yes, because that's the computationally expensive part. I mean,
yeah.
The other part is anyway infeasible if you don't do it, but so you have no way. Like this is the hard part. And there's packages like symbolic weatherburn.jl from Marek Kaluba, for instance, and they work very well. But again, they assume no knowledge, so that you don't give them anything, and they sort of do it blindly, which means that it has to go through all this. And so it doesn't scale amazingly. I mean, it's fast, but it doesn't scale amazingly for.
There were some I think there were some numerical algorithms to compute the block diagonalization.
Yes, but
when you don't know anything about the theory.
Yes, but they need.
Would that work?
They need a full spectral decomposition, and for these kinds of matrices, I don't think that's. I'm not sure about the linear algebra there, but I don't think that's feasible for.
They need what?
They need a full diagonalization of a big matrix, because you sort of, I mean, you talk about the matrix star algebra kind of techniques, yes. So what you do is you take a generic element of the matrix star algebra, which is big because it scales exactly with, like you lose all sparsity, you lose everything. You have just these huge matrices, and then you have to compute all the eigenvalues and also the eigenvectors. And I don't think this is, I looked at this, but I don't think this is gonna work for us. Yeah.
Thank you. Other questions?
So this probably sounds a bit like heresy in this room, but I wonder how an integer linear programming approach would perform relative to this.
I don't know, because I didn't even try, but it doesn't seem. Maybe Cordian can. I don't know if you tried this before with Frank. I have to say, you started this with Frank Valentin and another master's student who had to leave academia for what was this? I don't know. And then sort of the project died. But no, we didn't try. I didn't try the linear programming approach. Root. So I mean, these values here, you mean? These are from constraint programming. So there's Google's constraint program satisfiability solver, however they're called, and they can solve them exactly. But I don't really get over like 40s in reasonable time. So.
Okay, thanks.
So no more questions. So let's thank Luca again.